Hello, so we're now on to chapter 2. For those of you that have had chemistry already, this should be pretty easy. Some of you may be taking chemistry now, and some of you may be taking it next semester. One thing I would highly suggest is printing out and having a periodic table. You'll need it for chemistry either way, or maybe you have one for chemistry. So this is the objectives. Again, I'm not going to waste your time reading through all the objectives, but these are all the things that you should be able to do at the end of chapter 2. Today, we're basically only going to get through, or at least in this one, this unit, we're only going to get through a couple of them. I kind of try to chunk things up so that you're not staring onto a video for hours on end. And hopefully I can keep your attention at least for 20, 30 minutes. All right. Keywords. So these are vocab words that you should know by the end of the chapter. Again, I'm always big on making note cards or Quizlets or something, but you need to know what these terms mean. So I kind of have this broken down into 3 parts. One, we're going to talk about building blocks of molecules, and then chemical bonds, water, pH, and buffers. So I believe this first part is the first 2, and then water, and then pH and buffers. So introduction to chemistry of life. Matter is anything that occupies space and has mass. Matter may exist as one of 3 states. There's actually 5 states of matter, but we really don't usually talk about them. The 3 main or most familiar, I don't even say main because actually the most common in that the most abundant phase of matter we have is actually plasma. So we'll just say the 3 that we're familiar with would be a solid, liquid, and gas. So of course, you know, a solid has definite shape and takes up a definite amount of space. Liquid has a definite amount of volume, but it does not have a definite shape. It will fill the container in which it's in. And a gas, well, it does not have a specific volume or a shape. It will occupy or spread out to fill that amount of space available for it in whatever container it is in. We have the law of conservation of matter, which is matter is neither created or destroyed. We actually could talk about the law of conservation of matter and energy, because we can throw energy in there as well. And we will be when we start talking about energy in one of the next further down the road chapters. But we can't create or destroy matter or energy. We can just change its form or transform it. Matter may be changed. We can physically change it, you know, like I can take a piece of paper and rip it, right? I've changed it. I could chemically burn it, right? So I can take this paper and burn it. So that's something else I can do with it. But it's still paper, especially when I physically change it. It's still paper, I can still write it, it still has all its properties. Now, when I burn it, I have altered its chemical composition. And so now it's something different. You know, it's going to be ash, which has a very unique set of properties as compared to paper. So elements, that's what's on this little thing right here, this periodic table. This periodic table contains all of the elements that we are familiar with. And so they are unique types of matter. They have very specific chemical and physical properties. They cannot be broken down into anything simpler and maintain their characteristics. We know we can break down an element into its subatomic, like an atom of carbon will act and behave as carbon should, but I can break it into something smaller. I can break it into its subatomic particles, protons, neutrons, and electrons. But at that point, it no longer will behave like carbon. So our simplest unit that we can break down and keep it functioning as a unit of matter would be at the atomic level, so the atom. So elements, are unique. We use a single capital letter or two little letters. Most of them are kind of in English, but we have some really weird elements that don't make any sense. For example, sodium is Na, and you're like, where did we get Na from sodium? Well, the Latin word for sodium is natrium. So we've got a few, like potassium is kalium. Gold is like aureus or something like that. I don't know too much Latin, but so when you see these weird elements like lead is Pb, I think it's polonium or something. Don't quote me on that one, but it is the Latin words that we are basing those letters off of. So elements, so like I said, is the fundamental unit of matter. We have 96% of our body. And again, that's what we're studying life. So our body is made up of mostly 4 elements. That would be oxygen, carbon, hydrogen, and nitrogen. And of course, like I said, the periodic table has that complete listing of all those elements. Here is a table that kind of shows the elements inside humans versus the atmosphere versus the Earth's crust. So we have a lot of oxygen in us. A lot of us think of water, but water contains oxygen, right? H2O. We are a carbon-based organism. And then we have, of course, hydrogen and then some nitrogen. And we're going to talk about how these different elements make up different macromolecules and what we're made up of and where we get those percentages from in chapter 3. So here are some what we would refer to as some of the other elements and then our trace elements. And so you can see we talked about these up here. And then we have calcium, potassium, sulfur, sodium, chlorine, magnesium. And then we have some trace elements. That means they're in very small percentages, but we can look at that. We know like iron is in hemoglobin. Zinc is very important for the immune system, fluorine for your teeth, iodine for your thyroid to function properly. So even though they are trace elements, they are very important. So we have the structure of the atom. So we have our protons and our neutrons are in the middle. And then out here, we call these our orbitals. That is where we find our electrons. So the electrons is really kind of interesting because the electrons and the protons are attracted to one another. And so this force, this centripetal force that these electrons are spinning around kind of keeps them wanting, that force wants to throw them out. But the attractive force between the positive and negative charges are holding on to that electron. Electrons also want to keep away from each other. So notice we got an electron over here and they're kind of on opposite sides because opposites, we know that opposites attract, but the same charges repel. And you guys know that because you've seen like magnets and they have the attractive sides or their repulsive sides if you have the same poles together. Then we also know, well, then how are the protons in here? Now the protons are in here with the help of neutrons. Neutrons have no charge and they kind of act as I call them the peacekeepers. They act as the neutralizer in there, the neutralizer neutrons. They help to keep those protons from repelling each other and not being able to keep their nucleus stable. We also know that, so we talked about their charges. A proton has a positive charge, an electron has a negative charge, and then neutrons are neutral. Protons and neutrons have a mass of one Dalton or one AMU. They're both found in the nucleus. So our mass of our atom comes from the nucleus. Electrons have a mass, but it's so small. I always use the comparison as if you were to weigh yourself and then get off your balance and then pluck an eyebrow and weigh yourself again, you're not going to see any change. There is mass in that eyebrow, but not very much. So we do have mass in an electron. It's just, it's very, 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 very tiny. So when we look at the mass of an atom, we're counting up the number of protons and neutrons. So when we look at the box and that's the biggest problem I had. I would look at your periodic table here because there's two numbers. There's two main numbers in a basic periodic table. Some of the more complex ones have even more numbers. So your basic periodic table has two numbers. One's a decimal number and one's a whole number. And the one that's a whole number is the atomic number because it's the number of protons, and you cannot have like a half or a tenth or 2/10 of a proton. So in this case, it is 6. So for carbon, we have 6 protons. We will always have 6 protons in carbon. That's what gives it its property. And because we have 6, and I always call this my PEN, protons, electrons, neutrons. So my protons are 6. We assume all atoms are neutral unless we are told otherwise. So we know we have 6 electrons. Now my mass number here is the number of protons plus neutrons. And so since I already know I have, so again, protons plus neutrons equals mass. So I'm saying my mass is 12, and I already know that my protons are 6. So 6 plus what gives me 12, and that would be 6. So I know I have 6 neutrons. So that's how you would figure that out. Right, you need to be able to figure out the number of protons. You need to be able to do your PEN, and we're going to do a little more with that here in a minute. Now, isotopes, like some elements have more or less neutrons. And so you could have the same element, but with different mass numbers. So notice here, the mass number is 13. So again, protons plus neutrons equals my mass number. So here I'm saying it's 13. I don't know my number of neutrons. My number of protons is not going to change. So in this case, I would have 7 neutrons, right? So it's got an extra neutron in there. A lot of times when we have extra or not enough neutrons in there, the nucleus is not stable. And that can lead to radioactive isotopes. So we talk about radioactivity. So again, same number of protons, but different number of neutrons. So mass number is different. We can now some, I don't want to sit there and say radioactive isotopes are all bad. We actually use some of them for diagnostic tests. If you've ever had like a CAT scan, they put radioactive iodine in you for a tracer. This is a particular one that we have here. Most isotopes are called by, let me go back. So like this one would be called carbon 12. This one over here would be carbon 13. Okay, so most isotopes have their name, their element name, and then their mass number after them. Now hydrogen, we could say this is hydrogen. And that would be hydrogen 1, and this would be hydrogen 2, and this one would be hydrogen 3. But hydrogen's special, and so we actually gave it, each one of those isotopes have a specific name. So we usually just call protium hydrogen. That's just normal hydrogen. It has 1 proton, 1 electron. And then we have deuterium, and deuterium has 1 proton and 1 neutron. Again, it has to have the same number of protons or else it's not hydrogen anymore. And so because, again, remember we add up the nucleus, that gives us a mass of 2. Tritium has still 1 proton, but it has 2 neutrons. And so inside its nucleus, its mass is going to be 3. And that's why we call it tritium. We normally don't, we only deal with generally isotopes of hydrogen when it comes to nuclear power plants. We use water to cool the reactor, and we tend to end up getting what we call heavy water. And it's heavy water because we know we have H2O as water. But if we have more tritium or deuterium making up that hydrogen, it has a larger mass number, molecular mass number. So we refer to it as heavy water. But generally we'll use things like radioactive iodine, and we use that to trace different types of different maybe cancers and stuff like that using different tests. All right. Carbon dating, you guys have all heard of carbon dating. And so carbon dating, we use carbon 12 versus what's called carbon 14. Carbon 14 is interesting because you guys will learn about CO2 in the atmosphere, and we don't know if that carbon is carbon 12 or carbon 14. Carbon 14 is made up in the upper atmosphere, and plants cannot tell the difference. So they take that carbon in that CO2 and make sugar. And so that sugar, which is C6H12O6, has a certain percent of carbon 12 and the same percent based on the atmosphere, it's the same proportion of carbon 14. And then we eat the plants, or we eat the animals that ate the plants. And so basically what I'm saying is, in your body, you have a ratio of carbon 14 that's approximately equivalent to what's in our atmosphere. When you die, you're not eating anymore. And because you're not eating anymore, this carbon 14 is not stable, and it actually breaks down into nitrogen. And so by measuring the amount of carbon 14 in the fossil remains, we can tell how old a fossil is. And that's what we use for carbon dating. It takes about 5,000 years for, let's just say, for example, I don't want to get too much into the chemistry here. If you start off with 20 grams of carbon 14, it takes about 5,000 years to get rid of half of it. And so in another 5,000 years, we'd have another half, and then another half, and we keep going. And so we can only use carbon for so many years back, or else we run out of carbon 14. We have other radioactive isotopes we would use for really, really old specimens. So that's carbon 14, or carbon dating in a nutshell. And I already talked a little bit about, and we talk about in your book, some of the, like the PET scans and stuff like that. And make sure you read about it. That's stuff that, so for many of you guys, are going into the medical field. And so again, this has to do with isotopes. Those are elements that have more or less neutrons. They are not stable, and sometimes as they break down, they release radiation, and we can use that to identify structures that we're looking for, especially in soft tissue that we can't see, like on an X-ray. And then we have the periodic table. So like I said, make sure you have one of these periodic tables. Being able to use the periodic table is a very important skill. I'm going to kind of go through this slowly with you. And so if you can follow along with your periodic table, that would be helpful. All right. So we have what's called electron shells. Electrons, now, I don't want to say they're very rigid and in specific orbitals, because they're not. They're somewhat organized, but sometimes things go crazy. What we're saying is that we have a high probability of finding electrons in the following places. And again, they're trying to maximize the distance between themselves and minimize the distance between them and their protons that they're attracted to. And so most of you guys are familiar with this Bohr model, where you did the rings and you did the 2, 7, 14, and I don't even remember the rest because it's so not useful. All right, so I'm going to talk about valence electrons. So again, atoms are electrically neutral. We know we have the same number of protons and electrons. The energy shell, The first energy shell is the closest to the nucleus, and it can only hold 2 electrons. So if you were to look at the first row on your periodic table, notice there's only 2 elements, hydrogen and helium. So that's your first energy level or your first period. You go down to the second period or the second energy level. Notice we have 8 elements. Okay. And so with those 8 elements, all right, we start to follow what's called the rule of octet. The outermost energy shell, when we look at how many electrons are in that outer energy shell, that's called valent electrons. And those are the electrons that we are concerned with, because the electrons on the inner shells aren't going to be available for chemical bonding. Only the ones on the outer. All right. So, like I said, we have these orbitals, and I'm going to kind of go through them here with you guys. So, the first, like I said, the first energy level has hydrogen on one side and helium on the other, and it is organized for a reason like that. So the first thing I'm going to do is my pen, my PEN, because you need to be able to read that. You should read that the whole number in that box is 1, which means I have 1 proton, 1 electron, right? We have to have our charges balance out. Now notice that our decimal number, depending on how far out your periodic table goes, mine goes 1.0079. So that means my mass, we're going to round, my mass equals 1. So remember, my protons plus neutrons equal the mass number. So I already have 1 atomic mass unit. So my number of neutrons is 0. 1 plus 0 gives me 1. Now for helium, helium's whole number is 2. So that means I have 2 protons, 2 electrons. And when I look at its mass, oh my gosh, this one is so scratched up, is 4.003. So I'm going to round to 4. So my protons plus neutrons equal 4. I already have 2 protons, therefore my neutrons have to be 2. 2 plus 2 is 4. Now we also have this thing called Lewis dot structures. Now Lewis dot structures tell us the number of electrons on the outermost energy level. Now we only have 1 energy level right now. So with a Lewis dot structure, we're going to write the element symbol and a dot to represent that electron. Now this one has 2 electrons. So I'm going to put those together because they're in the same orbital. So we kind of look at, I'm just going to say, like, if I have element X, we're going to look at this like it's a box. And we have 1, 2, 3, 4 orbitals. Now that is true for all the periods on the periodic table. So all the rows going across except for the first period. The first period is so small, we only can have 1 orbital, which is why I stuck these together. So I have to put them together here. Okay, I'm going to move to the next energy level. All right, so my next energy level, my second energy level, starts with lithium. Now, if I do my pen, lithium has 3 protons, 3 electrons, and notice I have 6.9. 6.9, I'm going to round to 7. So that means I have 4 neutrons, because, right, protons plus neutrons equals my mass. Now, I said lithium has 3 electrons. Now remember, 2 electrons are going to fill up the first orbital. So How many do I have in the second energy level? I just have one, right? Because the first two electrons went into the first energy level. It's full. Now I have to move to the second energy level. So it'd be kind of like having, if I was to do the Bohr model, I would have my 2 electrons, and then I'd have my next energy level, and I'd have my third one. I don't care about that inner energy level. That inner energy level is not available for bonding. It is full. So I can't do anything with it. So I'm only looking at the outside. And with the outside, I have 1 electron left. Okay. So now I'm going to move over to beryllium. So beryllium has 4 protons. Ooh, let's see if I can do that. 4 electrons, and it's 9, so that gives me 5 is its mass. Okay, right, because these equal our mass. Now beryllium is going to have 1, 2. Now in chemistry, we do have specific places we do want to put them, but I don't care where you put them as long as you show me there are 2. Those are 2 valence electrons. I'm not saying there's 2 electrons only in beryllium. I'm saying I have 2 valence electrons. Valence electrons are, again, the electrons in the outermost energy level. And now I'm going to go to boron. Now, if you guys should get the hang of this. So boron is, I'm not going to do my PENs, right? It should be 5 and 5. So I'm going to have 2 went to the first energy level. So I have 3 left over. And then I have carbon, which we said was 6. Well, I've got 2 in the energy level. First one, 3, 4. That gives me 6 electrons total. So I have 6 valence electrons. And then I have nitrogen, which again, nitrogen, if we look at that, because we already did carbon, 6, 6, 6. Nitrogen is going to be 7, 7, 7. And so I have 7 electrons. Remember, 2 went to the first energy level. So I have 1, 2, 3, 4. Oh, now I have to partner up. You do not want to partner up electrons until you have all 4 of your orbitals full. So now I have to partner up. And then I have oxygen, which is 8, 8, 8. So I'm going to have 1, 2, 3, 4, 5, 6. And then I have fluorine, which hopefully you guys are seeing a pattern here, which is 9, 9. Is it 9? Let's see, 18. 9. No, that would be 10. So 1, 2, 3, 4, 5, 6, 7. And then we're going to get to the special one, neon. Neon is actually going to meet what we call octet, which is what our goal is here. Our goal is to meet octet. Octet meaning 8. And notice I have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. I'm at the end of my period because I am full. Because I'm full, I have to go to the next energy level for the next period. But before I go there, I want to explain what some of this stuff is saying. So what we're saying here is that lithium, because it has 1 electron that does not have a partner, lithium can form 1 bond, 1 chemical bond. Beryllium has 2 that are not partnered, so it can form 2 bonds. Beryllium has 3 bonds. Chemistry. Carbon 4. Now look at nitrogen. Nitrogen only has these 3 here. All right. So that's 3, 2, 1, 0. The noble gases are very stable. They cannot form any bonds. They do not have an unbound electron. All their electrons have partners to them. Okay. So when we talk about trying to be stable, all of these elements are trying to become stable like the noble gases or inert gases. That's the group in the last group. That's helium, neon, argon, krypton, xenon, radon. So it's all the ones on the last column. And those have all met octet except for helium. But remember, helium only has one orbital because it's so close to the nucleus. So it can only partner up the two. If we were to continue on to the third energy level, we would see the same pattern. We would see that sodium has one, just like, you know what, I'm just going to do this. Sodium, notice sodium is going to be underneath lithium. So if you're looking at your periodic table, so sodium also is going to have one. Magnesium is under beryllium, and it's also going to have two. And we can keep going. Aluminum has three. Whoop. And then silicon has four. And phosphorus has five. And so this is what the periodic table is talking about. We follow these trends. So when we look at the up and down columns, those are called families. I can't spell. Families. And families, we call them families because, oh my God, I really can't spell. Families. We call them families because they behave the same, just like you look like your family members. Okay. So when we talk about it, it's because they have the same amount of valence electrons. So if you look at the first column in your periodic table, all of those are going to have one valence electron. All of column 2 is going to have 2. Now skip over that middle chunk. That middle chunk is called the transitional metals. They have a different type of orbital, and that orbital is tucked in, so it's never on the outside for bonding. You'll get into more of that detail in chemistry. And then if we go to boron, its family, all of those will have 3 valence electron. All of carbon will have 4. Nitrogen will have 5. Oxygen's family will be 6. Fluorine 7. And then again, everything except for helium will have 8. That's what we want to do. We want to meet octet. Octet means we are stable. We're in our lowest energy state, right? So you need to understand how to read the periodic table. You need to be able to give me the pen. If I ask you how many protons, electrons, neutrons, you need to be able to do the Lewis dot structures, and we're not done with them. And that's what those dots, right? Like hydrogen. You need to understand what those dots mean for the next lesson. All right, if you have any questions, please feel free to reach out. If not, that is the end of today's, or at least this first part of chapter 2's lesson. All right, and I will see you in the next video.